Imagine a tranquil river flowing smoothly under the golden light of dawn. Its movement is predictable, steady, and calming. Now, imagine a storm rolling in. The river swells, twists, and churns into chaotic rapids. Its once orderly flow becomes unpredictable and complex. This transformation from calm to chaos is the perfect metaphor for what we call nonlinearity. Welcome to the fascinating world of nonlinearities, where small changes create extraordinary outcomes, transforming simplicity into complexity and revealing the hidden beauty of chaos. In simple terms, linearity is when the output is directly proportional to the input. Push twice as hard, and you get twice the result. This can be represented mathematically like this, where E is the output, X is the input, M is the proportional constant, and C is an offset. But nonlinearity is different. Here, the relationship between input and output isn't proportional. It's curved, twisted, and sometimes completely unpredictable. Where the presence of higher-order terms x squared makes the system nonlinear. Consider a spring. Pull it gently, and it stretches proportionally. A linear response described by Hooke's law, where F is the force, K is the spring constant, and X is the displacement. But pull it too far, and it resists differently or even snaps. A nonlinear response where higher-order terms like this come into play. Nonlinearity plays a central role in aerospace engineering. It governs how air flows over a wing, how structures bend under stress, and how control systems respond during flight. Understanding nonlinearity is the key to predicting and managing the complex behavior of aircraft. Let's start with aerodynamics. At low speeds and shallow angles of attack, the airflow over a wing is smooth and predictable. Lift increases linearly with the angle of attack, and engineers can model this behavior using this formula, where L is lift, CL is the lift coefficient, V is velocity, and S is the wing area. However, as the angle steepens or the speed increases, the airflow detaches from the wing surface, creating turbulent vortices. This introduces a nonlinear relationship in CL, especially beyond the stall angle, where alpha is the angle of attack, alpha stall is the stall angle, and K is a nonlinear constant. Now consider structural mechanics. Aircraft wings are designed to flex under aerodynamic loads, absorbing forces to ensure stability. At first, the bending is small and proportional to the applied force, a linear response described by this equation. But as the load increases, the wing deforms significantly, altering its shape and the forces acting on it. This nonlinear behavior can be captured by adding this higher-order terms, where beta represents the nonlinear stiffness coefficient. Aeroelasticity is where aerodynamics and structural mechanics collide. One dramatic example of nonlinearity here is flutter. This phenomenon occurs when aerodynamic forces and structural vibrations amplify each other in a feedback loop. If unchecked, flutter can lead to catastrophic failure. The governing equation for flutter dynamics is based on this term, where M is mass, C is damping, K is stiffness, and F arrow represents the aerodynamic forces. At critical speeds, the damping term C may decrease to 0, leading to an unstable nonlinear oscillation. Modern aircraft rely on control systems to ensure stability and maneuverability. But these systems themselves can introduce nonlinearities. For example, actuators that move control surfaces have physical limits, and when these limits are reached, the response becomes nonlinear. This can be modeled using this term, where delta is the control surface deflection, theta is the input command, and sat is a saturation function. Nonlinearity isn't just a challenge, it's an opportunity. By understanding and mastering nonlinear behavior, engineers can design safer, more efficient aircraft. It helps us predict turbulence, prevent catastrophic failures like flutter, and optimize control systems for modern aviation. Nonlinearity has enabled groundbreaking innovations, from flexible morphing wings that adapt mid-flight to hypersonic jets navigating turbulent conditions. It's the key to pushing the boundaries of what's possible in aerospace. To tackle nonlinearity, engineers use advanced methodologies like computational fluid dynamics, finite element analysis, and wind tunnel testing. Linear analysis provides quick insights, while nonlinear simulations capture the intricate reality of flight. These tools simulate complex behaviors and allow us to predict and refine performance under real-world conditions. Nonlinearity is everywhere, in the turbulence of the air, the bending of wings, and the pulse of innovation. It teaches us that the world isn't always simple, but it's through understanding this complexity that we achieve progress. Linear thinking is like driving on a straight road. Nonlinear thinking lets you navigate the mountains. Nonlinear behavior, though challenging, allows us to adapt, innovate, and discover solutions that simple systems cannot provide. Behind every smooth flight is a story of chaos and control, simplicity and complexity, woven together in the dance of nonlinearity. If this journey into the world of nonlinearity inspired you, don't forget like, share, and subscribe. I love your support. Together, let's uncover the secrets of aerospace and explore the beauty of engineering.